All right, in this video, I'm going to cover section 2.3, interpretations and axioms of probability. So let me go over section 2.3 using the textbook. In the front of this 2.4, while I'm going to cover using my lecture note with examples in textbook. So now you can see that in the first paragraph. So in this chapter, we introduce probability for discrete sample spaces. So discrete and continuous, we learn about those two terminologies. This is difference, right? So discrete means that the sample space uh, the is a finite set of outcomes or countably infinite set of outcomes. It means that we can count the outcomes in the sample space, or the number of sample space could be finite or infinite. Okay, and then now the probability is, you can see that in the second paragraph, probability is used to quantify the likelihood or chance that an outcome or random experiment will occur. So, for example, you can see that the chance of rain today is 30%. So that means that it's kind of the that probability give the kind of convert the uh, the chance of something to a degree of belief. Okay, so it's kind of the probability is yeah literally just the convert the chance or likelihood at the likelihood as numbers in the measurement. So now, but we're gonna see here here's big axioms. So as you can see that here right here, equally likely outcomes. So what that means, in a sample space, assuming that there are n outcomes in sample space, then the probability that the an outcome, we select an outcome, will be 1 over n. So whenever a sample space consists of n possible outcomes that are equally likely, the probability of each outcome is 1 over n. So that's the big axiom in actually classical probability. So what about the other type of, is there any other type of probability? Yes, but we'll see. We don't cover that one in this subject. Okay, so keep in mind this is a big axiom. So let's say example 2.12, a laser diodes. So assume that 30% of laser diodes in a batch of 100 meet 100. So it means that 30% out of 100, the how many diodes, I mean, let me finish the reading the first sentence. The 100 bit, the minimum power requirements of a specific customer. So then how many diodes has what? The satisfy the minimum power requirement? The 30% out of 100, which is 30 diodes, right? So now then, even by the way, so even though 30% of uh, out of 100 satisfy the minimum power requirement, that doesn't mean that the probability that we select, I mean, probability of each diode we select is still 1 over 100, which is 0.01 for each outcomes. Okay, for each diode, the probability we select on one diode is the whether or not that diode is the out of 30 we satisfy the minimum power requirement, whether or not that the probability going to be 1 over n. Keep in mind this. So if 1 over 100 in this case. So let me finish reading the problems. If a laser diode is selected randomly, that is so here random. This is really important. So in the B axioms, equally likely outcomes here. So we assume that the outcomes, um, I mean, the outcomes in sample space was selected randomly. Okay, so sample space was the chosen by random. Okay, so if a laser diode is selected randomly, that is each laser diode is equally likely to be selected. And then our intuitive feeling is that the probability of meeting the customer's requirement is zero point 0.3. Actually, that's right. But let's just mm, the uh, derive the point 3 that one based on the that action. Okay, and then also I'll introduce how to calculate the probability um, in the sense of statistic probability. Okay, so let E denote a subset of 30 diodes that meet the customer requirement. So what is this? E is event, right? Okay, what is event? Event is the what? The subset of sample space and the consisting of outcomes we are interested. Okay, so because here we are interested what? We don't interest. We're not interested in all of the diodes. We're only interested what the 30 diodes satisfying the minimum probability requirement, right? So because it contains 30 outcomes and each outcomes has probability 0.01. Yep. And then well, how come? Because of that one, classical, the axiom equal likely outcomes. So we conclude that the probability of E is zero point 0.3. The why? Because here, let me tell you. So because the probability E is gonna be 30 times zero point 0.01. It means that how many outcomes in there? 30, right? In event 30. So and then for each the probability for each outcome is what? 1 over 100, which is 0.01. So multiply that, we got zero point 0.3. So is that how we calculate the probability of event? Yes, but let me more formalize, okay, of this one. So actually, probability of event, this one is equal to, okay, that is equal to the number of um, outcomes in the event, okay, divided by number of outcomes in the sample space, So we use capital letter S for the symbol of sample space, right? So keep in mind this. This is the way to calculate the probability in a classical probability. Okay, so probability E is equal to number of outcomes in an event divided by number of outcomes in sample space. This is exactly the same as this one. Okay, so now next one. Probability of a second axiom. What, by the way, what is an axiom? Axiom is the big assumptions um, that we just upset. Okay, we just I mean we just promised that these statements are true without proof, without the argument. Okay, so this is more fundamental than definition. Okay, under the axiom, we define state the definitions, and then using definitions with some assumptions, we develop the theorems. Okay, so now anyway, so back to here, probability of an event for a discrete sample space. The probability of an event, noted as P of E, equal the sum of probability of the outcomes in E. Yes, right. So that is equal the sum of probability of the outcomes in E. So what that means? So let me explain this one by using that example 2.13 probability of event. So random experiment can result in one of the outcomes of A, B, C, D, and then with a probability 0.1, 0.3, 0.5, 0.1. Okay, so respectively. So now you see that the what give me a second. So now, see, they assume that the probability each outcome is different, right? The probability of A is, I mean, lowercase, the outcome A is not zero point 0.1, but probability of the second outcome B is not zero point 0.1, but this 0.3. Let's see. Now let capital letter A denote the event A, comma B, and then B, the event B, comma C, comma D, and then C, the event D. Now, probability A is what? Probability A going to be zero point 0.1 plus zero point 0.3, which is zero point 0.4. Okay, so that's what probability event says. Okay, so for this group sample space, the probability event E, denoted as P of E, equal the sum of the probability of the outcomes E. Okay, so now, but okay, but what about the formula? What I told you, that was I told you this is a probability in the classical the probability, which means that under the assumption that what we choose the outcome, the sample space was chosen as a randomly, okay, and then equally likely the selected, then the probably event gonna be number of outcomes in event divided by number of outcomes in sample space. Keep in mind this. For this case, for that case, each outcomes their probability is different like this. Then we calculate the probability of the event as like this. Okay. So now next one. Give me a second. Now example 2.14 manufacturing inspection. So consider the inspection described in example 2.11. Was it 2.11? Let's see, 2.11 is this. Remember that sampling without replacement. Okay. So a bin of 50 manufactured the part that contains the 3 defective parts and 47 non-defective parts. And then a sample of 6 parts is selected without replacement. Okay. Then that is each part can be selected only once, and the sample is subset of 50 parts. Okay. Now, how many different samples are there of size 6 that contains exactly 2 defective parts? Then we what? See, order matter? No, order doesn't matter, right? So the let's say the what let's just label the defective. Okay, the defect parts, which is defective part 1 to, let's say, part 1 to 3 are defective parts. Then we selected part 1 and 2, or we selected part 2 and 1. Do I count those two cases different, distinct? No, right? So order doesn't matter. So we have to apply the combination. Okay. So now you see, back to the right here. Okay, so from the bin of 50 parts, 6 parts are selected randomly without replacement. Okay, the bin contains 3 defective parts and 47 non-defective parts. Then what is the probability that exactly 2 defective parts are selected in the sample? All right, so now then, what are we going to do? See, the sample space consists of all possible unordered subset of 6 parts selected without replacement. So it means that what? We select the 6 parts without considering order and then without replacement, which is what? Then there's going to be, let me see, you can see that back to there. So that was the 3 times, you see that? Let's see. Yeah, right here. So right here, so the first one, how can you figure out? Yeah, so I believe you, maybe if some of you already go over the example 2.11, but let me explain about this. So the total number of way to select the 6 parts, then but out of 6, 2 parts are defective. First, we have to the count the number of way to select the 2 defective parts out of 3 defective parts without considering order. So we're gonna do 3C2. It's combination, right? So 3 to C2, which is 3. And then now we have to think about the number of way to select the 4 parts out of 47 non-defective parts. So that's going to be 47C4. So a combination of the what the 4 combination of the 47 to select the 4. Okay. So now then so 47 and 4, we got this one, 170, 78,000, and then 365. And then we now will apply the multiplication rule. So 3 times that number give us this. This is a total number of way or total number of outcomes in the sample space. Okay. So now then By the way, what is this? This is the just total number way to select the 6 parts out of 50 without considering, two parts as defective and then 4 parts as non-defective. Without considering that, just select the 6 out of 50 without considering order. So now, back to the example 2.14. Yeah, so now what are you gonna do? Okay, so back to the problem. What's the problem? So the bean contains 3 defective parts and the 47 non-defective parts. And then what is the probability that exactly 2 defective parts are selected in the sample? So now then we're gonna consider this. So you see that here selected randomly. So now we're gonna use this, the equally likely outcomes. It means that probability of event gonna be what? Probability event gonna be number of outcomes in an event divided by number of outcomes in sample space. Okay, so we just got number of outcomes in event, which is this. Okay, top one. And the bottom one is what? Is the number of outcomes in a sample space. In other words, the top one, the number in the numerators is what? The total number of outcomes or total number of way to select the 6 parts out, and then 2 part in the 6 parts, 2 parts are defective, 4 parts are non-defective. And the number in the bottom one is the total number of way to select just 6 parts out of 50 parts without considering, defective, non-defective. Okay, so now then the give me a second, and then what about this? A subset with no defective parts occur when all 6 parts are selected from the 47 non-defective one. Therefore, the number of subset with no defective parts is this. Um, give me a second. Yeah, so what do we have to? I think yeah, is this answer for the question here? I don't think so. So yeah, I think I just give just additional information. I think yeah. So now then, give me a second. Okay. So this is just number of way to select the all 6 parts, and then all 6 parts are non-defective. That makes sense. This is the 47C6. Okay. So that is just what 47 and then 6. That is equal to this. Okay. So and then the probability that no defective parts are selected, this what? That's gonna be 47 combination 6. This is a number of total number of outcomes in an event divided by total number of outcomes in sample space. That's the 50 combination 6. That is this. Okay. Yeah. So now, okay. So then axiom probability. So now here's the axiom probability. Probability is a number that is assigned to each number of collection of events from the random experiment that satisfy the following property. First one, key in mind is probability must be between 0 and 1. Okay. The could be 0. Okay. Could be 1. And then probability cannot be exceed 1, cannot be a negative number. Key in mind this. And then probability sample space gonna be 1. Yes. Okay, where S is the sample space. Yeah, and then it makes sense, right? Probability that we select an outcome in a sample space. What and then what is probability that what we select this outcome, then the outcomes belong to the sample space? 1, right? And then the probability event is between 0 and 1, yes, for any event E. And then for two events E1 and E2, with the E1 is E1 intersection E2 is empty set. What we studied that what in this case E1 E2 are called what a mutually exclusive event, right? In that case, probability E1 union E2 is equal to P1 probability E1 plus P of E2. What if E1 and E2 intersection of E1 and E2 are non-empty set? Then we have to subtract what probability of E1 intersection E2. Keep in mind this. Okay. So that is, yeah, that is equal minus probability of E1 intersection Okay, E2. Okay. So no. Okay. And then probably, and this at 0. Yeah. And then probably E complement. You see, remember that prime means a complement. So probably E complement is equal to 1 minus probably E. So when you solve problems, and then the problem says that find the probability of something, I mean, at least we do something. When you see the word at least, then most of cases you have to use this one. Okay. So they will see example of this one later. Okay. So then, for example, if the pro yeah, this is the example right there. So if probability of event E is zero point 0.4, and then our interpretation of a relative frequency implies that the probability of E prime is zero point 0.6. It makes sense, right? So because 1 minus zero point 0.4 is zero point 0.6. Furthermore, if the event E1 is contained in the event E2, you see that event E1 is contained in event E2, then probably E1 must be less than or equals probably E2, right? Okay. How come? Because think about this. The probability of what's this? The probability of E1 is what? Number of outcomes in E1 divided by what? Number of outcomes in sample space, right? And the probability E2 is what? Probably E2 is the number of outcomes in E2, right? And the divided by number of outcomes of sample space. Okay, say number of outcomes in sample space. So since the what E1 is subset of E2, so how many the number of outcomes in E1 must be less than, or let me say this a different way. Number of outcomes in E2 must be greater than or equals the number of outcomes in E1, because E1 is subset of E2. So that means P of E, because what N of E2, I mean N over E1, N over E, which one is greater than the other one? N over E2 is greater than N over E1. So these two guys are in the numerator, and then both fraction, they have same denominator. Then P over E2 must be greater than or equals P over E1. Makes sense, right? So that's the 2.3. Okay. So now next time I'm going to cover 2.4 using both textbook and then my lecture note. Let me stop it.